In mathematics, there exists an important concept known as matroids. These mathematical objects offer a powerful and elegant way to study structures that share the notion of independence, a concept already known from linear algebra. Matroids generalize some of the relations found in linear algebra, graph theory, geometry, combinatorial optimization, and more. Today, we will answer two of the most basic questions about matroids. What are they, and where to find them? Let us begin with some history. The concept of matroids was first introduced by the American mathematician Haslett Whitney in his 1935 seminal paper on the abstract properties of linear dependence. We will now read part of the introduction. Let C1 through M be the columns of matrix M. Any subset of these columns is either linearly independent or linearly dependent. The subsets thus fall into two classes. These classes are not arbitrary. For instance, the two following theorems must hold. A. Any subset of an independent set is independent. B. If NP and NP plus 1 are independent sets of P and P plus 1 columns respectively, then NP, together with some column of NP plus 1, forms an independent set of P plus 1 columns. Remember that. Furthermore, let us call a system obeying A and B a matroid. The present paper is devoted to a study of the elementary properties of matroids. Even further down, Whitney describes some very important properties of our theory. Although graphs are, abstractly, a very small subclass of the class of matroids, many of the simpler theorems on graphs, especially on non-separable and dual graphs, apply also to matroids. For this reason, we carry over various terms in the theory of graphs to the present theory. Remarkably enough, for matroids representing matrices, dual matroids have a simple geometrical interpretation quite different from that in the case of graphs. As matroid theory developed, many mathematicians, some of the most influential being William Tutt and Richard Radeau, both very famous figures, contributed significantly to its expansion, linking matroids to graph theory, lattice theory, and combinatorics. The classical definition of a matroid goes as follows. Let E be a finite set called the ground set, and let I be a family of subsets of E. Then the family I forms the independent sets of a matroid M if I is not empty, if some set A is in I, and another set B is a subset of A, then B is also an element of I. If B and A are elements of I, with the cardinality of B being smaller than that of A, then there is some element X within their difference, such that B union X is in I. As such, the pair EI makes a matroid. Of course, the elements outside I would be the dependent sets. The second condition we call heredity, or closure under subsets. The third condition we call augmentation. In some sense, it means that we can transfer elements from larger to smaller sets without losing independence. For an example, let us consider a given matrix with columns labeled A through D. These four columns, 4 vectors, will be our ground set. We can easily see that every pair of vectors forms a linearly independent subset of R2. In the context of matroid, they are independent sets. Because we are on a plane, both triplets, as well as all 4 vectors together, are linearly dependent. It is no coincidence that we started with a matrix. After all, every matrix generates matroids. But it's not true the other way around. One example of a matroid that cannot be represented by a matrix over any field is the Vamos cube. The problem of representability is one of the crucial questions in matroid theory. From the realm of linear algebra, you may remember the word base. Here, a base is a maximal independent submatroid of M, or equivalently, it is its maximal independent set, meaning that no additional element can be added to it without losing its independence. Every matroid has at least one base, but there can be more. For this matrix, every pair of columns forms a base. Bases completely characterize the given matroid, as every independent set is some subset of a base. This gives rise to another equivalent axiomatization for matroids. Let E be a finite set called the ground set, and let B be a family of subsets of E. Then B is the collection of bases of matroid M if the following properties hold. 1. The collection B is non-empty. 2. If B1 and B2 are distinct members of the collection B, and some element X is in B1 minus B2, then there exists an element Y of B2 minus B1 such that the set B1 without X but with Y is a base. The second axiom is called the base exchange property, and it's quite easy to see when it holds. It may be harder to prove that both systems actually describe the same matroids. Another important definition would be that of a rank. The rank function of a matroid maps sets to the cardinality of their largest independent set. For the whole matroid, rank is just a number, written RFM, the size of the largest independent set. In our example, to no surprise, the rank of the matroid is equal to its matrix rank. We may expect that in general. We are familiar with many operations on matrices, but if by chance we decide to, for example, look at only some of their columns, we might stumble upon a minor. Given a matroid M, its minor is any matroid N that is obtained from M by a sequence of restrictions and contractions. Well, for restriction, it's basically creating a new matroid from a subset of the ground set, where independent sets are a subset of the original ones. Circuits remain circuits, more about them later, and where subsets of this new matroid retain the same rank as they would have in the original. Contraction is a little more complicated. Here, we also make a new matroid, but this time we remove some subset of the ground set, and then, for the independent sets, we check if their independence is connected to the deleted subset in the original matroid. I know this may sound somewhat abstract, but it works just as you may expect. Now, let's turn to graph theory. Let's start with a little game. We have 4 vertices, 4 solitary vertices with no edges. Now I would like to add more edges to the graph so as not to make a loop. I'm going here. For now we want the edges to stay connected. Here. Now I need to go here. What now? No matter what edge I add now, I will get a cycle somewhere. At this point the game concludes. But wait a minute, what did we get? A tree. Each previous step also generated trees, while this one is specifically called a spanning tree. Spanning just means it hits all vertices. Great. Now I will modify our game slightly. This time we don't have to connect the edges. So here I go. I put an edge here. Now here, because I can. Look, we no longer have a tree. Instead we have a forest. We add the last edge and we are done. Again, we get a spanning tree. For 4 vertices, there are 16 labeled trees. From each such tree I can take an edge. This, of course, will not add a cycle. I can exchange edges between any 2 of these trees, and they will still remain spanning trees. Well, to be fair, we could also be working with spanning forests. On the other hand, I can't add a new edge without introducing a cycle to the graph. This sounds a bit like a base of a matroid, whose ground set is the set of edges and whose independence relation is being acyclic. This is a fact, all acyclic subsets of edges of graph G are independent sets of graphic matroid MG. Equivalently, the independent sets are edge sets of forests of G. Here we have a graph. For simplicity, it too has 4 vertices. It has 5 edges. It also has 3 cycles. What about these cycles? A circuit is a minimal submatroid contained in no base, or it is a minimal dependent set. It now follows from definition, and confirms our suspicion, that no independent set will have a cycle as its subset. These two can be used to axiomatize the structure of a matroid. This set of edges meets our definition. Removing any one of them will turn our circuit into a tree. This collection, on the other hand, does not meet our definition. For our last example, I would like to talk about one of the most beautiful objects in finite geometry and in mathematics overall, the Fano plane. Named after the Italian mathematician Gino Fano, it is the smallest possible projective plane. The Fano plane is often denoted as PG2-2, the projective plane over the finite field with 2 elements. If we follow the 5 axioms of Fano geometry, we will end up with 7 special points and 7 special lines, where each line contains exactly 3 points, each point belongs to 3 lines, and every pair of points is connected by exactly 1 line. First, there exists at least 1 line. Now every line has exactly 3 points on it. But not all points lie on the same line. There must be a line connecting every 2 points. But each of these new lines contains exactly 3 points. These 2 points lie on a line, and the same line connects to the 3rd point. Same on the other side. Finally, we do the same for the 7th line. The same structure can be written in the language of matroids. Then, the 7 points are our ground set. The empty set, all single points, all pairs of points, and all non-collinear triples make our family of independent sets. The same triples are our bases, and the collinear triples make up the circuits. You can try to reproduce our 5 axioms by looking at these sets. There is also another way of constructing the Fano plane without direct reference to this exact axiomatic system. It is also a method that can be generalized to other projective planes. We will start a dimension higher, with the affine geometry AG32. So we are in 3-dimensional affine space over 2-element field. We can think of it as a set of 8 triples, x, y, z, where each coordinate is either 0 or 1. There are 28 lines in this geometry, and 7 of them go through the 0 point. We will identify them as 7 one-dimensional subspaces and write them in a matrix form by just taking the non-zero components. Look how beautiful this arrangement is! But what we really get is 7 projective points of our projective plane. We projected lines from 3 dimensions onto points in 2 dimensions. So there we have it. The Fano plane can be represented as a matrix. On the other hand, remember that we are working modulo 2. In any case, we need that minus 2 equals 2 equals 0. Working over a 3-element field would lose us a circuit. This line here. For this reason, our matrix is a binary matrix, and our matroid is a binary matroid, only representable over GF2. It is in no way regular. Having all this information in mind, I will end by stating, for your own consideration, a particular theorem. Following the work of Tat, a binary matroid, the one exemplified by our Fano plane, is regular if and only if it does not contain, as a minor, either the Fano matroid or its dual. So I really like matroids. It only took a few definitions for us to be able to combine notions from linear algebra, graph theory, and finite geometry. There is much to be said about dual matroids, transversal matroids, partitions, different axiomatization systems, applications to combinatorics, but I will leave that for another occasion.